stress, strain and Young's modulus. Let's start with tensile stress. So tensile stress, measured in pascals, is the tensile force or tension divided by the cross-sectional area. Now tension is one of those quantities we need to get our head around to start with. On this picture here I've drawn just one force, F, acting down. And if that was the only force on this cylinder, then the cylinder would accelerate downwards. We know that's not the case. So we know that this cylinder, if it remains in equilibrium, must also have a force upwards on this cylinder which has the same magnitude, F. And any point in this cylinder would feel a force downwards, F, and a force upwards, F. We call that force the tension. Now the cylinder had no mass, we supported it rigidly on the top and didn't suspend anything underneath it to stretch it, we just left it with nothing on it, there'd be no tension in it and the force would be zero. If we then started to add weights onto the bottom of this cylinder to stretch it, then every 1 Newton we add is a Newton of tension within this cylinder, and that's what F equals. With the cross-sectional area, just be careful that if you are given the diameter of a cylinder of, for example, a wire, then you would use this equation to find the cross-sectional area. Don't confuse diameter with radius. For the stress, the tensile stress, to be in pascals, the tension, the force, has to be in newtons, and the cross-sectional area has to be in square meters. And with wires, that can be a very, very small cross-sectional area indeed. So don't be surprised if you have very small numbers for your cross-sectional area and therefore very large numbers for your tensile stress. The tensile strain is the extension divided by the original length. Look on this diagram here, you can see that original cylinder which has been extended by being stretched. The extension I've labelled here X and the original length I've labelled L. And so extension divided by original length is the strain. Now you'll notice that extension is a distance and original length is a distance. And because we're dividing a distance by a distance, the strain has no dimensions. And in fact, it's usually given as a unitless quantity. So for example, if we have an extension in centimeters, it's sensible to give our length in centimeters as well, so that the centimeters cancel and we are left with a decimal. Sometimes strain is also given as a percentage. Young's modulus of a substance is the tensile stress divided by the tensile strain. And usually it's given in gigapascals because usually it's a very high number indeed. So here is a typical question asking you the Young's modulus of a wire. We are given the diameter of the wire and we are given the original length of the wire. We are then told that the wire extends 16 millimeters when we have 890 newtons of tension. Well, let's start by finding the tensile stress, which is the tension divided by the cross-sectional area. The cross-sectional area was 1/4 pi d squared, so I've substituted that in here. Now the next step is very important. When I've substituted the numbers, I know that my diameter must be in meters and my force in newtons for my tensile stress to be in pascals. So I have written 1.0 times 10 to the negative 3 as the diameter and then squared it. And that gives me 1.133 gigapascals. Now let's calculate the tensile strain, which is the extension divided by the original length. And I've chosen to substitute the numbers in millimeters. And because the units are cancelling, I didn't bother to write them. And that comes out at about 5.714%. Now to find Young's modulus, we divide the tensile stress by the tensile strain. And we show our steps. We write down our equation, we substitute our numbers, making sure we have the correct prefixes, and then we calculate the answer. And with this fictitious made-up material, we've got 19.83 gigapascals, not very high at all. And so that is how you solve a problem and calculate a Young's modulus.